nos avisas. Bien.
Listo.
Bien, buenos días a todos, todo el público latinoamericano. Esto es la red LAFMAT, Red Latinoamericana de Física, Materia Condensada y Ciencias de los Materiales, red LAFMAT. Como todos los sábados tenemos la palestra de un invitado, en este caso del casi doctor, ya por sustentar, el señor Chinna Kandula, de la Universidad de Hyderabad. El señor Chinna Kandula está haciendo su doctorado en la Universidad de Hyderabad, en India, bajo la supervisión del profesor Pratap Kolu, un gran amigo nuestro, que es miembro de la Royal Society, representando en la India, en el Reino Unido. Chinna Kandula ha publicado artículos en el American Chemical Society, muy buenos artículos. También un capítulo del libro también en un American Chemical Society, y el día de hoy nos va a dar una charla que es titulada Structural and Magnetic Properties of Lu-doped Ytterbium Manganeso Oxygen 3. Bien, recordar que la red LAFMAT está conformada por miembros de universidades latinoamericanas, tales como la Universidad de Zulia, en Venezuela, la Universidad Nacional de Colombia, en Bogotá, Colombia, la Universidad Federal Rural de Río de Janeiro, en Brasil, la Universidad Federal de Pernambuco, en Recife, Brasil, el CIMBESTAB de México, la Universidad de San Martín en Argentina, Universidad San Sebastián en Puerto Montt, Chile, la Universidad Católica del Norte, Antofagasta, en Chile, la Universidad Nacional Mayor de San Marcos, en Perú. Bien, no creo que me haya olvidado ninguno. Por momentos voy a hablar en inglés también para presentar al profesor Chinna Kandula. Profesor, el investigador Chinna Kandula he's going to submit his dissertation soon, a PhD dissertation, the University of Hyderabad. He specializes in physics, chemistry, and material science. He has published some high-impact publications in the ACS Omega, also a chapter book in American Chemical Society. It's a very promising researcher with a high prospect. Has been doing his thesis under the supervision of Professor Pratap Kolu, who is a very good friend of us, and Pratap Kolu is also going to participate in the second Latin American Conference on Superconductivity and Magnetism, which will be held in Lima, Peru, at the University of San Marcos from 23 to 27 of October. Entonces, todos también están invitados a participar en la segunda conferencia latinoamericana en superconductividad y magnetismo, que se llevará a cabo en la ciudad universitaria de la Universidad Nacional Mayor de San Marcos, en Lima, Perú, del 23 al 27 de octubre del 2023. En la página web de LAFMAT puede encontrar toda la información necesaria. Perfecto. Well, Chinna Kandula, yes, welcome. Sir. And you can start.
Thank you, sir, for giving an opportunity. So, good morning to everybody.
You can start sharing your slides.
Okay. Can I share my slides now?
And you can start now.
So, it is visible to everyone, sir?
Yes, it is. It is. Go ahead.
Okay. Shall I start now, sir?
Yes, at the end of the talk, the members will ask you questions, okay?
Okay, sir.
Okay, cheers.
So, good morning to everyone. So, myself, Chinna Kandula. So, presently I'm working as a CSL Senior Research Fellow under the guidance of Dr. Pratap Kolu from University of Hyderabad from India. So, first of all, I want to thanks to all the committee members who have invited me as a talk. For it is a good opportunity for me to discuss my work in these seminars. So in this present talk, I would like to tell some of my research work, whatever I done in last few years. Like one of the part I will discuss here. The main talk, here, the title of the talk is Structural Magnetic Properties of the Lutetium Doped and YB site in YbMnO3. So this is my brief introduction. So now I'm going to discuss my plan of talk. So in this present context, I want to give the introduction about the multiferric because this material is a multiferric, not in room temperature, but when it comes to low temperature, it exhibits both multiferric properties. And I want to discuss some of the motivation why I'm taking this work. And later I will discuss structural and magnetic properties. This is the main topic of this entire plan of talk. And some of the conclusions that are from that structural and magnetic properties of the lutetium. So everyone knows about what is multiferric. Multiferric, generally the properties, some material have the ferromagnetic, some material have ferroelectricity. So and we have to synthesize the material which have the both simultaneously exhibit these properties in the same phase. So that's why these materials are not available in nature. So we have to synthesize ourselves. So this is the brief introduction about the multiferric. A multiferric is a crystal that can be defined multiferric when the two or more ferroic orders that are united in the same phase of the sample. That means in one sample can be exhibit simultaneously ferroelectricity as well as ferromagnetism. If that material we called as multiferric, these are the several applications in nowadays. So like before going to applications, I want to know what is the multiferric, because we know the multiferric is more than one. That means more than one means what? The ferroic order, like ferromagnetic, ferroelectricity. If any material possesses any of the two, that is called multiferric. So before going to what is ferromagnetism, a magnetism that can be switchable by applied magnetic field. So whenever applied the magnetic field, then if the magnetism is developed inside the material, that are called ferromagnetic material. So that phenomenon we call as ferromagnetism. Similarly, the ferroelectricity is a electricity that can be polarized by applied electric field. That is called ferroelectricity. And similarly, ferroelectricity is a deformation that can be switchable by applied stress. So if any material possesses out of three, any two, that is called, we treated as multiferric material. So this is about the brief introduction of the multiferric material. So come to my motivation, why I'm taking this YbMnO3 for my investigation doping effect like this. Generally, these RMNO3 structures give a lot of physical applications like magnetic-electric effect and the magnetic effect properties. Generally, this application for magnetic-electric, I want to study this magnetic-electric effect applications. This RMNO3 shows different properties. It depends upon the what is the R now. So this is the R is the rarest element in this manganese RMNO3. So if the R is radius is higher, that means it is a rhombohedral. It gives a rhombohedral structure. So generally, this is meant for the R values, U, JD, and TB, and lanthanum something. So if it comes to very small ionic radius like holmium, YbM, lutetium, this shows hexagonal structure. So that means if you have higher ionic radius, this are the rhombic, but it comes to a small ionic radius, it is hexagonal structure. These hexagonal structures exhibits multiferric order. So that's why we are taking a small ion radius of rare earth elements like lutetium for doping on YB side. Then we have to see how the structural change and magnetic effects will be changed when it comes to very low temperature, from room temperature to lower temperature. So these are the very potential applications in data storage and capacitor and magnetic cooling like that. So these are some of the literature of the hexagonal magnets RMNO3. So we know that the hexagonal material have the lattice parameters A and B are same, C is the different, but AB are 90 and C is 120. So this is the unit cell characterization. So These are the some of the literature I show here. So, but my main concentration on YbMnO3. So in YbMnO3, the from literature shows the lattice parameter, lattice constants like initial constants like A is equal 6.0 to angstroms and C like this. So it shows the that Niel's temperature at around 87 Kelvin. So it is effective magnitude movement is 64. So compared to lutetium, so lutetium manganese oxide, it comes to 5.2. So that means why lutetium shows, that means it is a diamagnetic nature. So that's why this effective magnetic movement must be reduced. So I want to check whether it is happen or not like this. So why I'm selecting this only investigation of YbMnO3, the previous literature when I go through it, so much later work was done on YbMnO3 and YbMnO3. Maybe few works was done on YbMnO3. Some of my seniors who did in this university as a PhD, they are investigated some of the work, HO, helium, and some of the manganese site and YB site. But my present, I want to see the how the structural change in magnetic properties with a low ionic radius compared to higher. So the next slides, I generally, in order to prepare any compound, we have to adapt to different types of methodology we have. So I adapted the solid state method, which is available in our laboratory, as well as I want to produce the bulk. So whenever you have to produce the material in bulk manner, so the solid state is the best option. So in this, I want to prepare the lutetium doped on YbMnO site. So these are the methodology I adopted. So the psychometric amount of the ytterbium oxide and lutetium oxide MnO3, these are my initial precursors chemicals. These are the taken in oxide form. These are the very purity also very high, because we are purchasing this oxide from Sigma Aldrich with the 99% 99 impurity, 99% 99 purity samples we are purchased. So because in solid state, in order to get the good quality of the sample, the purity is must. So that's why these are my initial precursors or chemicals I purchased from the Sigma Aldrich company with the 99.99% purity. So initially these samples are weighting according to psychometric ratio. After that, it is handling at 1000 degrees centigrade for 24 hours in air atmosphere. After that, there are several grinding processes are there. So because why are you taking the grinding process? Because the grinding process itself gives the homogeneity. If you do the more time grinding, that means the sample get uniform to over all the entire surface. That entire whatever the compound we have, that maybe give the better homogeneity if you go for higher rate of grinding. So after that, I will again, after making the taking the sample, I'm pressing into pellets. So here when I'm making the pellets, I apply around 7/10 of the pressure in order to get a good pellet. Again, it is centering at 1200 degrees centigrade for 24 hours. Generally, in solid state, we need high temperature in order to get eliminated the impurity peaks and not mixing proper phase. So generally, in solid state, we have to go up to 1200. This is the rarest. So generally, based on the previous literature, I optimized some of the conditions where I got a single phase. So these are the optimized condition I got it. Finally, I take the, after XRD, I confirm it. I went for 1400. Why I'm going to went 1400? Because in order to increase the density of the material, if the density of the material is good, that will give the good morphology, as well as when we take the dielectric also, it may be give the better results. So that is one of the reason I went for higher centering at 1400. Again, these pellets, I take the XRD. So these are the XRD analysis. Whenever we prepare some sample, we have to check whether that sample is good at or not based on the XRD only. So we know that I know the what is the parent compound that is XRD patent by literature. So I want to see whether it is formed single phase or not. You can see here. So the first figure in the top of that is a YbMnO3. That is the parent compound. I synthesized that in my laboratory, and from reticle refinement also I did it for this by using expert I-square plus software, which is available in our university. So there is no single that means the sample is perfectly formed. And after reticle refinement also, it shows that means every peaks, majority peaks is matched. Their Miller index is also matched with my compound. So there is no other phase. This is the hexagonal structure is confirmed from the XID. After that, lutetium also for 15% doped is happen on YB side. So it is same things happen, but the exact peaks may be shaped because of the dopant. So in order to know how much lattice parameters of the unit cell will be changed, that can be done after this one. So the next slides I will show that here the reticle refinement results. So this is the parent compound. I took the database from the Crystal Open database. So this is my parent compound. What is the prepared with 15%? The lattice constant value, if you see it, it is reduced. And overall volume also, because the parent compound comes around 360.6749 angstrom cubic, but it comes to 15% of the lutetium dopant on YB side, it is reduced. That means a small amount of the reduced because of one reason, because this ionic radius of the lutetium is smaller than the YB. Because of that reason, the volume is sink overall. So that's why the entire volume of the unit cell of the lutetium doped is reduced as compared to parent compound. So I calculated tolerance factor. Why do I calculate tolerance factor? And the goodness of the fit also I will show here. It comes from the parent compound 1.7 and 1.1. You can see my plots. So how much it is good each and every peak over there. So the tolerance factor here I calculated. Generally, the perovskites YbMnO3 structure is perovskite if it is tolerance factor lies between 0.8 to 1. Generally, the cubic is the tolerance factor is 1, but perovskite lies between 0.8 to 1. If that value is the lies between, so our values also same lies between on that. So it is a good perovskite structure also. This can be visualized in Vista also. So I visualize it, but as of now, I am not putting here that figure. Next, I went for characterization of the Raman spectroscopy. So the Raman spectroscopy also is a fingerprint for the structure analysis. So I observed all the active modes of what are the active modes that are present in the Raman in the parent compound as well as 15% of the dopant. For parent compound, we can see that a prominent mode is at around 679. I got it for parent compound. It is labeled as in blue color. But in 15% it is shifted towards right. That means it shifted towards the right means the red shift is happened. This is red shift is happened because of the sinking of the volume that is confirmed by XID itself. So you can see here. So in XID shows that volume is reduced. That means the material volume overall sink. That same thing is happening in the Raman also. I took the Raman from at room temperature. That room temperature shows that means the same trend has the XID also. So from these two things, you have to see that whenever you dope a small ion element, ion reduced element on the heavy element, automatically the entire volume of the unit cell element must be reduced. So that is the same trend is happening in my case also. So next I will study the FECM analysis. From FECM, I want to check the purity of the sample. From this purity of the sample, and as well as I want to see what is the morphology. Generally, in solid state, we won't get up to nanoscale level, but because up to micro level, we will get it because in solid state, that is the morphology we can observe. So here, when you go for lutetium doped, that grain size may be increased when compared to YbMnO3 on a 10 micrometer scale. So from EDAX, it shows that the purity of the sample YbMnO3 is the same because there is no other foreign element is not there. What are the elements that are present in YbMnO3 that are there? I want to know from ImageJ software how much grain size may be formed in that. So I calculated by ImageJ software from histogram plots. So the image grain size is found to be around 5.79 micrometers. But in comes to lutetium, so it is all from EDAX also. Lutetium also shows here from EDAX spectra that the grain size is increased from 11.91. That means when you dope this one happen, this is the general trend we have observed when you dope something. Generally, the grain size of the particle may be increased. So this is same trend I have got in this my lutetium doped on YbMnO3 also. So next, I would like to go to the structural properties is over. Then I want to move the magnetic properties of that. Before going to magnetic properties, we have to discuss what type of the nature of the material. So that's why I want to give the brief introduction about some theory behind that, how the plots look like for the different types of the magnetic materials. So here I shows the susceptible versus temperature. So for diamagnetic, it shows negative value because that diamagnetic, the susceptibility is very negative. So that's why it gives a straight line below T. That means that indicates negative value. For paramagnetic nature, is like a curve like this. A blue color curve is over there, a green color curve, and antiferromagnetic nature is a yellow color like that. It increases like this. After that, is sharp will decrease. This is the called Niels temperature. That means where the temperature at which that uh, yeah, antiferromagnetic nature become a paramagnetic. So that's the temperature. So like ferromagnetism like this. So if it comes to the same thing, so chi versus this is the from the literature I took from the nature. So when chi versus temperature, if you follow the Curie-Weiss effect, so it shows like this. So that yellow color here. So I want to observe what nature and if you in order to know what nature of the material, whether it's para or ferro or antiferro, you have to take 1 over chi versus T. So if the T, that means the line we got in one over chi with respect to T versus T, it shows if the yellow one it shows 0, that means it is passing through 0 means this is a paramagnetic nature. But if you get positive value of the y x intercept, it is called ferromagnetism. That means Curie-Weiss constant. And if it negative Curie-Weiss constant, there is a antiferromagnetic nature. So here I took the MT measurements. In order to find susceptibility versus temperature, we have to take the MT measurements. So everybody knows when you take the MT measurements, so there is the 2 types of or 3 types of the modes we have to take ZFC and FC. So I measured the ZFC and FC for my samples. In the ZFC and FC, one was the state measurements. Yeah, because in ZFC generally the samples at room temperature we have to cool fast without applying the field. Here I will show here. Generally at room temperature, without applying a field, their sample is cooled up to 2 Kelvin. After that, the field is applied over there. The data is collected from 2 Kelvin to 30 Kelvin around room temperature. This data we call the ZFC data. So here I plotted ZFC, but not FC, but both are almost simultaneously coincide exist. So that's why I show here only ZFC data. So that means the field cool, that means after reaching room temperature, again they applied the field, again they cool the sample from 2 Kelvin by applying the field now. That's why it is field cool. The data is collected when applying field. That is called from 300 Kelvin to 200 Kelvin. This data we called as field cooled. So here I show the MT data in ZFC mode. So we know the susceptibility, it is the ratio of M over by H. So we know how much magnetic movement. We have to divide here the field is applied around 100 oersted. So I got chi versus T. It is similarly, you have to see the same behavior like this. That means it is a paramagnetic nature as well as paramagnetic nature. So in order to know what nature it went to from room temperature to lower temperature, you have to take 1 over chi versus T. It gives a better understanding whether it follow antiferromagnetic nature or paramagnetic nature. So for that, I take 1 over the chi. Here the chi versus T. But next slide, here it shows 1 over chi versus T. Here it shows the linear because when you take the linear, because the Curie-Weiss shows the linear part. So from this curve, the linear part is around 150 to 300 Kelvin. So I take the linear part of that and I plotted here. But this is touch the y-axis around minus 183.52 K. That means it shows antiparamagnetic nature when it comes to very low temperature. From that, I calculated the Curie constant and effective magnetic moment and where Curie's Curie-Weiss constant also. I got the Curie constant around 4.90316 and effective magnetic moment or Curie constant can be related by this expression I took from the literature. This is based on the Langevin theory of the paramagnetism. So the effective magnetic moment I calculated is 6.259 for my case. So the Curie constant, I got it this one. So again, I calculated my sample. It is experimentally, it is found that effective magnetic moment, it comes around 6.259. I want to cross check for theoretically also. For theoretically, I want to calculate like this. So this is the formula I adopted from the literature, from the previous published papers from my laboratory. So I calculate the effective magnetic moment. Every calculation I show here, because in lutetium plus 3 is diamagnetic, so that's its net magnetic moment is must be 0, and YB plus 3 oxidation state comes 4.57. So finally, at the end of I got it, the effective magnetic moment is 6.44 μb. That means my theoretical value and experimental value are almost close. So sometimes the experimental values is lesser than theoretical values. That trend is observed in many papers. So I'm good enough. So my sample synthesis good way, and the effective magnetic movement, theoretical and experimental, is found that they are good agreement with two values. So this is the effective magnetic movement I calculated. So this is the theory. Why I'm taking like this? Why I got the C is 1 hour slope here. I will explain the from literature. We know that everybody the Curie constant Curie law. So the chi is equal to C over by T minus TW. So if we take that is reciprocal over there, it comes Y is equal to mx plus C. So here I show the equation 1. Then I compare Y is equal to mx plus C, that mx plus K. It is the straight line which have the intercept K. So compare that way. So I got the slope is equal to 1 by over slope, 1 over by slope, and the y-intercept is equal to comes to Curie constant over by C. That means 1 over C is again slope. So I will put it Curie constant is equal to minus y-intercept by slope. That's why I calculated the theory. So whatever the results I got it, I compared the literature. So they have found that they are good agree with the previous results of the parent compound. But nobody did it so far for lutetium. I'm the first guy doing this lutetium doping. So next, I want to see how the material, I take the MH loop of that MH measurements for my samples. So meanwhile, I'll take from empty data, I find it low temperature. It comes the Curie constant is calculated. That what you call Curie temperature is calculated. So at Curie temperature, low temperature, it comes around 3.09 Kelvin, and these samples generally at room temperature is a diamagnetic, but when it comes to very low temperature like 2 Kelvin, the magnetic phase is changes. So you can see here the trend. I took the measurement from field versus H. So when 40 Kelvin, see it is a sky, it is a diamagnetic like that. So almost paramagnetic. When it comes to only 2 Kelvin, it shows some stress. So that means at 2 Kelvin, the magnetic phase of the sample changes from this paramagnetic nature to around some super paramagnetic nature. I calculated the retentivity coercivity of the sample at 2 Kelvin that are inserted here over there in the left side of the figure. At 2 Kelvin, the same figure is taken out, and how much retentivity, how much coercivity, how much saturation, because after that is small amount of the saturation over there. So I calculated about this one. So I got this type of the value. So the magnetic coercivity comes around to 8.02 EME per mole, and retentivity comes around 220 3.05 Oersted, so into 10 to the power 3. So I took that after this sample never shows that much. You can see the data also. I plotted with the data points also. So it never behind that value, it never saturated still. So that's why I put it saturation. Okay. So this is the results I got from the entire research on magnetic properties of my sample. From the reticle refinement, the sample showed this hexagonal single phase structure and confirmed by XRD and reticle Raman. And this is what type of the structure is hexagonal, and the space groups comes to P63CM. From FECM analysis, the average grain size was found that compared to parent compound, the grain size for lutetium dope is higher because of this doping effect. And I take the measurements for MT. So it shows the super paramagnetic nature without saturation shows at 2 Kelvin. You can see here. And I calculated theoretical and have experimentally effective magnetic moment of the mesh sample. These are the found that the good agreement we almost because 6.2 and 6.4, that means very small 0.2 around it. That means the my sample theoretically and experimentally verified that it is good enough. So the sample okay. These are the measurements I got it. So I want to give my acknowledgement to my CSIR. This is one of the top research funding for our research scholars from India. So I'm selected for CSR. Right now I'm working as a senior research fellow. So I thanks to Professor YbMnO3. So he's my mentor. So yeah, for supporting this financial support through NASI Allahabad Research Center as a honorary scientist. And I would like to thanks to my guides, so my mentorship as well as my well-wisher friend, Brother Dr. Pratap Kullu. So he also provide me whatever things I need, and he helped me support for funding of my research. And I thanks to Dr. Sujay Chakravarti for MT measurements. What are the magnetic measurements we have? Because our university don't have this facility at low temperature as of now. So I asked them. So he's also scientist at Kalpakam now. So I thanks to my senior Dr. Sati Babu. So he's working as assistant professor, and my labmate J. Rothiranjan for helping to analyzing the data whenever I got, for synthesizing some help wherever I got. So I thanks to each and everybody who are indirectly helped me for my research going to good more. So this is thanks to everybody for your attention. Hello.
Thank you very much, Chinna. Thank you for your nice talk. Well, I would like, now we are going to start with the round of questions.
Okay, sir. Okay.
From the panelists here. I would like to start with a Colombian team. Okay. I don't know if Professor David Landines or Jairo Roa are here. If not, maybe Ximena can ask questions because she's working with some perovskites about that as well. Okay. Ximena?
Well, good morning. Thank you for the talk. In this moment,
can you show your camera or?
No, I have a problem here with my camera. Okay. I'm sorry.
You are at home, okay?
Yes. Well, maybe with what is the program that you use for XRD analysis?
This is the Export I-Score Plus.
What? Excuse me?
Export I-Score Plus. I-Score Plus.
Hi-Score Plus.
Plus, yeah, that is the Export I-Score Plus. So that software is a licensed software available in our laboratory.
Okay. What is the
that version I am using 4.9 version, ma'am.
Okay, is near to the theoretic.
This is assigned to because our university purchased 3 licenses when I installed the XRD machine from Pan Analytical. That is the company is provided that software. So along with the machine. So recently we purchased that software from that company.
Okay, thank you.
Okay, thank you very much. Thank you very much, Ximena. We are going to continue with the questions from the University of San Marcos. I think it's Professor Ángel Bustamante. Ángel.
A ver si lo planteo ahorita tengo una duda en la presentación. ¿Es posible to making using, por ejemplo, European error or the Johnny radius need to change this atom Ethereum or and so on.
Please, sorry, sir, pardon. So please tell me. So I did not understand your questions. Please, can you repeat one more time? Sir, excuse me, pardon. Please repeat the question one more time. So I did not understand properly.
No, my question is about to using European air, air
European. That yes. That
European
That is also diamagnetic. So I'm also working on the same sample. So I am also take some of the measurements. So right now I'm also working on the same sample. European is also +3 is a diamagnetic, but when experimentally it found that its effective magnitude comes around 3.4 or 3.5 around. So I want to cross check that one. Theoretically, it found that 0 because the L and J value almost similar for that value because we know from Landau G factor. So the effective magnitude comes around 0 for EU +3R.
Okay.
So I'm also working on that same sample. So I also censored the sample. Right now I'm measuring the measurements also done. So maybe I will analyze the later that sample. So
Okay, thank you, Angel. Okay, thank you, Angel Bustamante. We are going to ask. Now we are going to move to Professor Stuart Holmes from the University College of London and the University of Cambridge. Stuart.
Thank you, Chinna, for your talk.
Yes, sir. Please.
I did actually know Pratap when he was in Cambridge. He actually measured some of my devices.
Okay. Actually, these measurements was done by SCID, sir, which is not available on our campus. So I asked the one scientist from who are working in CSIR. This is a Council of Scientific Industrial Research. This is one of the big funding agents. So only few facilities we have in India. Maybe the SCID is maybe rare for us. So I wait for a long time. Luckily, I got last time. So I censor my samples. So I wait for until I got measurements. That is the only thing. So but whatever the results I expected, so I got it. So I'm happy with that. So
thank you. I have some technical questions about your presentation.
Okay.
The first one is, you mentioned in your introduction that these materials are multiferroic, so they have
yes,
ferroelectric and ferromagnetic. But for your particular materials, you only discussed the magnetic properties. Do these materials have ferroelectric properties or ferroelastic properties? In other words, are they really multiferroic?
Yes, sir. This is a ferroelectric when it comes to low temperature, not in a room temperature.
So you don't have access.
That facility is not there. Based on the literature, I told this one. So, but if you measure the PV measurement at room temperature, it not shows any loop. But when it comes to very low temperature, like our liquid helium temperature, that shows it is loop or PE loop.
Maybe a collaboration with your work, you can measure the devices at lower temperatures.
Yes, sir. I need a low temperature measurement.
That would be good to confirm that they are multiferroic.
Okay.
Yeah. The other technical question I have is the grain size is dramatically different when you add the dopant, the LEU.
Yes,
what causes that grain size to change? Normally, if you put some doping in, perhaps the crystal breaks up to smaller domains. You seem to have larger domains in the alloy.
Yes, sir. And it shows hexagonal face also. Maybe I will show in my slide here. So maybe I'll go there. Yeah, we can see here. So I maybe move on the cursor. So it shows exactly hexagonal structure. This is how the 6. Yes, sir. But I can't see in the parent compound. It may be on the same scale. Maybe if its scale is more, maybe I will, because in order to compare both the results. So I took the image in the same scale. So I want to synthesize again for this YbMnO3. I want to see it because here I'm take the very small quantity because this is rare earth. So I may make a 1 or 2 pellets. So I break the pellets. That's why some over there, there's some cracks is also over there. Maybe I will make a small diameter of this pellets. So then I will want to see. Actually, I expected that this grain size, most of the figures increase because of dopant, but I want to go through it, the literature. So as of now, why it has happened that much increment has happened, I'm not sure about that confirmation.
That's okay. Thank you. I'll just finish with one more question. You said in the introduction that the crystal structure is hexagonal, and then at height for perhaps larger doping atoms, it goes over to orthorhombic. Do the orthorhombic crystals have multiferroic behavior?
No, sir. The orthorhombic only hexagonal structures only gives the ferroelectric material, that is multiferroic behavior, but orthorhombic won't.
Yeah. Okay. Yeah. Thank you. That's yeah. Thank you. Thank you for
that's
your
talk. I want to synthesize in an hexagonal only, so that is only gives the multiferroic behavior.
Yeah. Thank you. That's answered the question. Thank you.
Okay.
Nice talk. Thank you.
Okay.
Thank you, Stuart Holman, for the questions. Now let's move to Chile. Sergio Conejeros Espindola from the University Northern Catholic University in Antofagasta, Chile.
Hi, thank you very much for your nice talk, Dr. Chinna.
Yes,
I would like to know, I have a technical question about the magnetic susceptibility when you show I think the first derivative of the susceptibility of the magnetic susceptibility with respect to the temperature. Can you show that slide, please?
I will show you now, sir. Yes, you can see here. So
yeah, I have a question there because you're indicating a near temperature, right? This is antiferromagnetic material, but you don't
yes.
but you don't have the typical behavior of the antiferromagnetic behavior. So because when you were explaining about the different magnetic material behavior, so you show the typical antiferromagnetic behavior that you have something like that.
Yes,
but here you don't have that behavior. So can you give more details about that, please?
Okay, from here I show the behavior of the different chi versus T different materials over here. So if you see in this figure, the paramagnetic as well as antiparamagnetic in nature, it comes similar, but the sharp drop after increment, sharp drop over there. Maybe this is the threshold limit, so maybe that may not be drop over there. So I want to know whether it shows super paramagnetic or it went to antiparamagnetic nature. So in order to confirm it, the only one way you have to do that, you have to take 1 over chi versus temperature. Then we can find the Curie Weiss constant. If you found that Curie Weiss constant is positive or negative or 0, based on that we can confirm that if it is positive and maybe it's 0, if it is 0, it is a paramagnetic nature. If it is antiferromagnetic, the Curie constant comes negative. So my case, I took like this. So I plotted, so it shows antiferromagnetic nature. So that means the negative Curie constant, I got it. So we can see this interpolation from because in this, whenever take 1 over chi versus the temperature, we have to identify the linear region where it goes. So after zoom it, I show this is the one from 150 to 300 Kelvin. It shows a linear part. I show this out to the plot also. I show all the parameters I show here. Whatever the data I got from X origin, when I do it plotting, everything I put it here to understand well. So see after extrapolated, you can see it is also touch the same thing. I calculated experimental also. It shows when I extrapolated also, it shows the negative intercept of the temperature. That means it is antiferromagnetic nature when it comes to very low temperature.
Okay, yeah, now I understand. Thank you very much for the clarification. Okay, nice talk.
Okay,
thank you again.
Thanks, sir.
Thank you very much, Sergio Conejeros, from the Northern Catholic University of Chile in Antofagasta. Well, now we are going to move to Venezuela, to the University of Zulia, Professor José Fermín.
Hola, Luis, gracias. Thank you, Chinna, for your talk.
Thank you, sir. Thank you for.
I have no questions for you, but I want to wish you my best wishes for your future work.
Yes,
Very
sir.
nice. Thank you.
Okay. Thank you, sir. Thank you for your encouragement for me.
Gracias, Luis.
Okay, gracias, José Fermín. Well, now, Chinna, when you know that your supervisor, Professor Protocolo, in
Yes, sir.
2016, he has been in Peru in the first version of the International Conference or the Latin American Conference on Superconductivity and Magnetism in Lima. And at that time, one professor was helping him in guiding from the hotel to the university every day.
Okay.
And he became friend of your supervisor. And now
sir.
he's here. He's from the Federal Rural University of Rio de Janeiro. He's Professor Isaías Gonzaga Oliveira. Isaías?
Obrigado, Luis. Thank you, Luis. Thank you very much, Chinna, for your talk. I have
Thank you, sir.
I have one naive question. This manganite shows magnetic and structural transitions. So, have you investigated magnetocaloric properties of these magnetites?
Sir, please pardon, sir. Please once again repeat the question.
Magnetocaloric potential, magnetocaloric effect.
Caloric effect. Yeah. That means you have to. As of now, I'm not putting here, so I want to find the entropy measurements. So that was not done for this sample. For U sample, I was done. So we know that relative cooling power we can calculate it from the entropy. That is the maximum delta entropy into that is a full width of maximum. We will get some Gaussian curve over there. So from Gaussian curve, we have to find the relative cooling power. The relative cooling power is related with the expression that change in entropy in maximum into the full width of maximum of that Gaussian curve. So maybe that data is not with lutetium. So maybe European I have it, but as of now it is I can't put it in the slide now. So based on this relative cooling power, we can see that how much effect. If your relative cooling power is higher, that sample is very good application in the magnetic effect, at least at low temperature. Nowadays, we need a magnetic refrigerator is one of the base trend of trend. So my samples may be application in space also. So I want to search a new application where it is applicable based on what are the properties I studied so far.
Okay. Thank you very much.
Thank you, sir.
Go ahead, Luis.
Okay, thank you very much, Isaías Gonzaga Oliveira. Well, you know Professor Protocolo as well, right? He's supervisor of Chinna. Wow.
Yes, I know.
Okay. Now let's see if there is question from the public. Eliana, are question from the public? Okay, Eliana. There is no question from the public. Well, now let's Chinna.
Yes.
Every Saturday we organize online conference like this.
Oh, yes, sir.
And
I'm happy with that, sir. You are invited me as even though I'm a student at level. So I'm happy to share my feeling. This is my first international conference or seminar talk, whatever it may be. So I did completed my master from University of Hyderabad. So after that, I cracked the CSR. I joined here as a research fellow under Pratap sir. So I'm happy with that. This conference it may be benchmark for my career.
in 2019, I have been in Vellore, and Professor Patakolo was there as well in India.
No.
You have been in that conference as well in
No,
Vellore?
sir. Whenever your students came to India, some of your students came to India. At that time, I was there.
Okay. Well, let me tell you what are and to the public, please, the next talks, okay? On June 17, the talk is Estudio y selección de materiales como nueva tendencia en ingeniería para la inteligencia artificial. El moderador será José Fermín, que nos tiene que pasar el nombre del speaker. June 24 is Professor Amar Prasad Yadav, is from the Tribhuvan University in Nepal. July 1st, the talk is from Efraín Viesca Villanueva from the University of Coahuila in Mexico. The moderator is Arturo Martinez from Simvestab. On July the 8th, the talk will be from Professor Konstantin Karatiunov from Russia. The moderator will be Professor Isaías Gonzaga Oliveira, and we are going to have also as a panelist Professor Mauro Doria. Well, you are always invited to participate as well. And maybe you want to add any words to say goodbye to any people, Chinna?
Yes, sir. Actually, I want to collaborate with some of my research related these things. So as of now, our university don't have the facilities at MT like magnetocaloric application like entropy versus temperature and that. So if anybody is willing to help me in that way, so I'm very happy with that. So maybe my research may be good for me. So I sense most of the samples which are required for this type of the measurements. So as of now in India, very less helium, liquid nitrogen available, and very few people are there to take the measurement. It takes a lot of time for me. So anybody is willing to help in that type of the measurements, I'm happy with that. So that is the request from my side as a student level. Sir?
Well, I think that we through Professor Pratapkolo, I think that you can find the correct collaborator to do that measurements. Okay.
Yeah. So I'm interested in material science as well as this physics. So most of the part I'm working on the magnetism area. So in the condenser matter, because this is my specialization area when I doing my master's also.
Okay. Well, now you can stop sharing your screen, please.
Okay.
And now everybody opens their camera to say goodbye to Dr. Chinna. Okay. The camera. Okay.
Hi, sir.
Thank you, Chinna.
We are going to cut. Everything is end. Okay. Thank you very much, Chinna.
Thank you, Chinna.
Thank you, sir. Thank you for everyone. So to giving me such a beautiful opportunity in my career. So I never forget this opportunity to share my entire work as a part of my work to discuss such a views a knowledge person rent off. So I'm at student level. It is a good opportunity for me.
Okay.
Luis,
Okay, José Fermín, sí, tenía que decir un comunicado.
le acabo de pasar el nombre y una foto del conferencista a James.
Excelente. Muy bien. Okay. Próximo sábado entonces. Goodbye. We are going to cut now. See you.
Okay, sir. Thank you, sir. Thank you for everyone. Okay.
See you.
Goodbye.
Hasta luego a todos, que estén muy bien. Goodbye.
Goodbye. Okay.